Everyone, in this video, we are going to learn software engineering unit number 2, that is software design principles and system architecture. In this, we will cover modularity, cohesion, coupling, functions oriented design, data flow diagrams, structure charts, and transform and transaction analysis design review. So what is our unit roadmap? We will see design principle. Unit number means first part. Second part is cohesion coupling. Third is function oriented design. And fourth one is data flow diagrams. Fifth one is structure charts. Sixth one is transform transaction analysis. Seventh one is documentation and review. So we will start with what is software design. So we will see in this software design is the bridge between what the system must do, requirements and how the system will be built, code. It translates the SRS into a blueprint of components, data, interfaces and algorithm. In this we will see correctness, efficiency, understability and maintainability. In correctness we will see it satisfies every requirement in SRS. And efficiency, we will see optimal use of time, memory, and resources. Understability is easy for other engineers to read and maintain. Fourth one is maintainability. In this, localized low cost changes over the system life. From requirements to code, we will see first one is requirement in SRS, then architectural design, then detailed module design. Fourth one is interface design, and fifth one is implementation of code. Now we will see the basic principle of software design, that is abstraction, refinement, modularity, architecture, control hierarchy, and information hiding. In abstraction, we will see focus on essential characteristics while hiding implementation, detail, procedural, and data abstraction. In refinement, we will see top-down process, elaborate a high-level statement into successive level of details, stepwise refinement. In modularity, we will see decompose the system into independent, well-defined modules that can be built and tested separately. So in modularity, we have seen how we decompose a system into independent, well-defined modules that can be built and tested separately, means it's tested separately and built. In architecture, we will see the overall structure of modules and the manner in which they interact with one another. In control hierarchy, we will represent the organization of modules and implies a hierarchy of control between them. In this we have seen how it represents the organization of modules and implies a hierarchy of control between them. In information hiding, we will see modules reveal as little as possible about their inner working. Implementation details are hidden. So let's start with modularity. It is design principle. In this, dividing software into separately named independently addressable components, modules that are integrated to satisfy the problem requirements. Cost versus number of modules in this graph is given. How decomposition is going, integration is going, and total cost we will see. Why modularize? First one is easier to develop, test and debug in isolation. Second one is enable parallel work across a team. Third one is localize the impact of changes. Fourth one is promotes reuse of well-defined components. Fifth one is but too many tiny modules raise integration cost, hence the optimal point M. Now let's see cohesion and coupling in measuring modularity. The two yardsticks used to judge how well a system has been decomposed into modules. What is cohesion? It is intra-module strength, degree to which the elements inside a single module belong together. How closely related and focused the module responsibilities are. Goal is to maximize cohesion. A highly cohesive module does one well-defined job. Example, a module that only validates user input. So, how much high cohesion is there, then good design will be. In coupling, we will see intermodule dependency. In this, degree of independence between module, how much one module relies on or is affected by another. Its goal is to minimize coupling. Loosely coupled modules can change, be tested and be reused with minimal ripple effect on others. Low coupling is there, good design is will be. Types of cohesion. In this, we will see 7 levels ordered from weakest to strongest module design. So, let's see. First one is coincidental. Elements grouped arbitrarily with no meaningful relationship at all. Logical is elements perform similar operations selected via a control flag. Example is one module for all input output type. Third one is temporal. Elements are related only by timing, all executed at the same phase. Example is an initialization module. Procedural. Elements grouped because they follow a certain sequence of execution or control flow. Fifth one is communal. Elements operate on the same input data or produce the same output data. Sequential. Output of one element is the input to the next within the same module. In sequential, we are seeing that output of one element is the input to the next. Means output, when we give the output of one element, then we are getting input to the next one is within the same module. Functional one is every element is essential to performing a single well-defined task. Ideal means ideally we are performing every elements single by single essentially. Now we will see types of coupling. There are 6 levels ordered from strongest to weakest dependence. First one is content. One module directly modifies or relies on the internal data or code of another, most severe form. Common. Multiple modules share access to the same global data area. Third one is external. Modules share an externally imposed data format, communication, protocol or device interface. Fourth one is control. One module passes a flag or control parameter that dictates another module. In internal logic stamp. A composite data structure example is whole world is passed when one part of it is needed. Now data modules communicate using only simple elementary data parameters weakest or best form. Now we will see cohesion and coupling measuring module independence. A module is independent when it can be understood, changed and tested with minimal reference to other modules. Independence is judged jointly by cohesion and coupling. Means in this we are seeing that a module is independent when it can be understood, changed and tested with minimal reference. In this, when we give minimal reference to the module, it will be independent and it can be understood, changed and tested to other modules. Independence is judged jointly by cohesion and coupling. Means independence will be judged generally by the type of cohesion and coupling. Low coupling, then poor cohesion, high coupling. No, let's see. Low coupling is there. Worst design zone, then focused module, but tangled. In third one, independent but unfocused. Ideal design zone. Poor cohesion, high coupling, then high cohesion, low coupling, and poor cohesion, then low coupling. Benefit of independent modules. First benefit is errors stay local, easier fault isolation and debugging. Second one is modules can be developed by different teams in parallel. Third one is a module can be reused in other system. Fourth one is changes to one module rarely ripple into others. Fifth one is testing is simpler, modules verified in isolation. Now we will see design trade-off. Maximizing cohesion and minimizing coupling can pull design decision in opposite direction. Good design is a balance, not an extreme. Decision push toward A, push toward B, and trade-off. So design will be module size. Push toward A is fewer, larger modules. Push toward B is more smaller modules. Trade-off is large modules raises internal complexity, tiny modules raises integration and call overhead. Now reuse versus speed. Push toward A is generic reusable modules. Push toward B is purpose built fast module. Trade-off is generic code adds flexibility but can cost performance and clarity. Now decision is data sharing. Push toward A is shared or global data fast access. Push toward B will be past parameter encapsulated, and trade-off is global data speed access but increases common coupling and hidden dependencies. Now fourth one is decomposition depth. In this, decompose further, find control, and push toward B is stop decomposing simplicity. Trade-off is deeper decomposition raises integration cost. Recall the optimal point B. Now we will see function-oriented design. In this, a top-down approach that decomposes a system around the functions it performs, modeling how data flows and gets transformed as it moves through the system. The core idea is first we will process function, it will get the output data. Now, when input data is given to process, then output data will be uh, outside, means give to output. Every DFD process transforms input flow into output flows. The essence of function-oriented thinking. Top-down decomposition. The system function is refined into sub-function, layer by layer. Data flow diagram. In this, the primary modeling tool is shows data movement, not control flow. Structure charts. In this, derived from DFD, data flow diagram to show module hierarchy and how modules invoke each other. Fourth one is centered on data flow. Unlike object-oriented design, the function, not the object, is central. Now we will see DFD symbols and notations. Four symbols are there to describe every DFD. Let's see the example. First one is student external entity, then validate login process, then student records data store, then login credentials. It is data flow. Then in this external entity, source or destination of data outside system scope. In process, we will see transforms informing data flow into outgoing data flow. Data stores in this a repository of data at rest, a file, table, or databases. In data flow, we will see an arrow labeled with the data that moves between components. Now we will see context diagram level 0 DFD. In this first library management system is example. In this we shows the entire system as a single process together with an all external entities it exchanges data with. It fixes the system boundary before decomposition begins. In this, first we will search request or book availability of member, then new catalog publisher in this report request or MIS report admin, then issue return entry or find details librarian. Now we will see DFD labeling. A single context diagram is progressively decomposed into greater drill, greater details. Each level exposes more sub processes while preserving the data flows of the level above. Level 0 is context diagram, level 1 is top level DFD, level 2 is detailed DFD, level 3 is as needed. Level 0 is whole system as one process, external entities only. Level 1 is system exploded into 3 to 7 major processes. Each process from level 1 exploded further. Level 3 is decomposition continues until each process is single and simple function. Golden rule in this is the input and output data flows of process at one level must exactly match its exploded DFD at the next level. This is called balancing. Now we will see rules for constructing DFD. First one is every process must have at least one input and one output data flow. And second one, we will see data cannot flow directly between two external entities. It must pass through a process. Third rule is data cannot flow directly between two data stores. A process must mediate. Fourth rule is data cannot flow directly from an external entity to a data store or vice versa. Fifth rule is every process must have a unique, meaningful verb based name. Example validate order. Never process 1. Sixth rule is process numbering must stay consistent across level. 1.0 explodes into 1.1 and 1.2 and so on. In seventh rule, we will see a data store name should describe its content, not its implementation. Example student record, not table underscore 04. Eighth rule is keep each DFD to 5 to 9 processes for readability decomposes further if a diagram grows too dense. Now we will see structure charts, component and notation. In this, a hierarchical chart derived from the DFD that shows how modules can one another and what data or control passes between them at each call. Notation is module rectangle, then calling relationship is this straight line and arrow sign is right side means data coupling open arrow data. In this sign is control couple dash or flag. This sign is conditional call. This sign is loop or iterative call. Example process order. In this, we have seen validate order and update inventory. No, first one is get order, then validate order, then update inventory. Now, we will see module, hierarchy and control flow. In this, structure charts arranged modules in layer of control. A top module coordinate middle modules manage subtasks and bottom worker modules do the actual input or compute or output work. In this main control module is executive. In this we will see main control module by error handler and output controller. Output controller you have two types, format reporter and print receipt. Now of executive coordinates, we will see compute controller and input controller, calculate total and apply discount. In input controller, read record and validate input. These are the manager subtask control. Now we will see transform analysis. In this DFD2 structure chart, used when a DFD has a clear uniform flow, incoming data is transformed through a central process into outgoing data, maps DFD with this shape into a structure chart. In this, afferent incoming branch, then central transform, then afferent outgoing branch. In this, main control, then get welded input, transform data, then produce output. First one is identify the afferent and efferent data elements, the point of maximum abstraction. Second one is draw the boss main control module at the top of the structure chart. Third one is add one subordinate module for each of input, transform and output branches. Fourth one is factor each branch further module by module, then until it maps to a single DFD process. Then, transaction analysis. In this, used when a DFD has a transaction center, a single incoming flow is routed to one of several possible processing paths based on the type of transaction. In this, first is transaction request, then analyze and dispatch, then it will give deposit, withdraw, transfer, and balance inquiry. These are the four main type after analyze and dispatch. Then maps to transaction dispatcher. It will do deposit handler, withdraw handler, transfer handler, and inquiry handler. Now transform versus transaction analysis. Transform analysis is one continuous pipeline. In this, input process output used for sequential uniform processing. Transaction analysis is one dispatcher routes to several alternatives path used when a system branches by transaction type. Now, design documentation. The software design documentation is the formal record of every design decision, the reference used for implementation, testing, and future maintenance. In this, we are having six parts. First one is introduce and scope. In this, purpose, goal, and boundaries of the design. Second one is system architecture. In this, module hierarchy, structure charts, and subsystem view. Data design. In this, data stores, schemas, file or databases structure. Fourth one is module specification. In this, purpose, interface, cohesion or coupling nodes per module. Interface design. In this, APIs, UI screens, external system interface. And sixth one is DFD, all levels, context diagram through level or detailed DFD. Now we will see design review techniques. In this, design is reviewed before implementation begins to catch defect when they are cheapest to fix. In this walkthrough, informal or developer led, designer presents the design to peer step by step. Then informal setting encourages open discussion. Third one is goal. Surface obvious error and get early feedback. Fourth one is no formal sign off or metrics captured. In inspection, we will see formal moderator led Fagan. In this first one is a trained moderator leads a structured is scheduled session. Second one is reviewer used checklist to hunt for defect classes. Third one is role assigned moderator, reader, recorder, and author. Fourth one is defect lodged. Formally, reinspect may follow. Now, key takeaways we will see recap of all these. First one is design principle. In this, abstraction, refinement, modularity, and information hiding drive good design. Second one is cohesion increases then coupling decreases the universal test of module independence of and design quality. Third one is DFD model data flow. In this context diagram, then in this level DFD balanced across level built by fixed rules. Fourth one is structure charts, model, control. In this module hierarchy derived from DFD via transform or transaction analysis. Fifth one is review before you build. In this walkthrough and inspection catch design defect at their cheapest point. So in this, we have seen all the unit number 2 topics line by line, and in next part we will see and most important MCQs for your exam. So till then, take care and goodbye. Thank you. Have a nice day.